Hello, everybody. My name is Aleksandar Kuzmanovic, and I will explain. I will present the bloXroute Labs, which is a blockchain scaling project trying to help scale all the blockchains out there in the world. So, without much talk, let me try to explain what is the big problem that we are trying to solve. So, the big problem that all blockchains in the world are facing is the scalability. Okay, how many transactions per second can a particular blockchain support? And despite all the buzz and all the great news and all the science coming from many different exciting fields, the reality is quite different. Bitcoin, the first blockchain system, currently supports 3 transactions per second. And Ethereum, the second largest blockchain, the second leading blockchain, supports 10 transactions per second. And I hope I'm not going to spend a lot of time to convince you that these transactions, this current capacity is nowhere close to where it needs to be in order to support the real world applications. So just to give you examples, so just for Visa today supports 5,000 transactions per second. And if you take another example, consider the number of cars in the United States of America. If each car is filling the gas only once a week, then just for that particular application, there's going to be needed 450 transactions per second. Okay, and so at this point, whenever we talk about blockchains, we are speaking about these super futuristic applications such as machine-to-machine communication and micropayments. And in a case when, in a scenario when the reality is far from these numbers, it is a little bit embarrassing to talk about all these future applications. So the key position of my presentation today is to state that the networking layer, or layer 0, is the key to solving this particular problem. I would like to say that this holds not only for the first generation blockchain projects and blockchain systems, but this is true for every single blockchain system in the world. Okay? So to introduce the problem, let me quickly give you an example of Bitcoin. I'm sure most of you know about what the problem is here, but let's still go through this together so that we can actually understand what is happening here. So in Bitcoin, a transaction is 540 bytes long. Okay, this is somebody from point A to point B sending money. Hence, there is a transaction of 540 bytes. There is a parameter in Bitcoin which is the amount, the size of the block, and how frequently the block can be sent. And in Bitcoin, for security reasons, this is set to there is a 1 megabyte block which is sent every 10 minutes. Okay? And so if you do some calculation here, it's easy to understand if you divide 1 megabyte with 540 bytes, that becomes 900 transactions. Okay? And so 1900 transactions divided by 10 minutes, that is, if we turn the minutes into seconds, that becomes 1900 transactions divided by 600 seconds. This leads to the famous 3 transactions per second. Okay? So now looking at this very simple example that I'm sure everybody is aware of, it becomes obvious how we might be able to change the situation here. So the key parameter here is how long can the block be and how frequently can we send the block into the network. Okay? And if you look at this example, it says 1 megabyte block every 10 minutes. Why don't we change this particular relationship, right? So for example, why don't we send 300 megabyte block size, megabyte block every 10 seconds? On one hand, this would surely resolve all the blockchain scalability problems because this gives you huge amounts of TPS rate. But at the same time, this is not smart to do because it's not possible to send 300 megabytes over 10 seconds. That's too much to be done in the current world. But people tried something similar. And basically, there was a famous case where a block which was 30 megabytes long was sent to the network, but it made to the other location only after 20 minutes. And everybody was surprised. How could it be that this 30 megabyte block takes so long to reach the other part, to propagate through the network? Well, I'm a professor of computer science, and I will now try to tell you why is it possible that it takes 30 megabyte block to propagate for 20 minutes on the internet, despite the fact that we live in the 21st century. I take some blame for this because I'm one of the guys who was involved in designing some of the things in the network, a very tiny part, but still this is what it is. So what is the problem here? Well, look, consider a peer-to-peer network, and the miner sending a block from one side to its peers. In this particular slide, I'm only showing 3 peers because that was possible to sit on this particular slide. In reality, there could be 8 or 16 peers or something like that. So that miner on the left side could be in China, for example, and it is connected to other nodes that are, for example, in Europe or in US or in other parts of the world. Actually, in a blockchain system, it is good that there is this randomized communication such that blockchain nodes are connected randomly in the network. However, once you are sending a large block from one part of the world to the other part of the world, the performance may not be as good as you can hope for. And the reason for this is that the networking is such a field where the worst component in the system is defining how bad that entire connection is going to be. And hence, it takes just a little, just one narrow link on an end-to-end path to significantly slow down this entire communication. Now, the problem is that this is just the beginning of the entire issue. Why is that? Because here we are talking about a peer-to-peer network. Okay? In a peer-to-peer network, the information is propagated in cascades. Okay? So first I send to my peers, then my peers send to their peers, and so the information is propagated in this way through the network. But this means that the number of locations, the number of places where things can go wrong significantly increases. Okay? We don't have to wait for a single connection to be poor. If at least one of these connections is poor, then it's possible that the entire communication is not going to look good. And moreover, because we're talking about a peer-to-peer network, as you can see in the middle, if something is wrong with the machines in the middle, peers in the middle are not well provisioned, if they malfunction, then this affects the entire peer-to-peer network communication, and hence this is a big problem. Now, next I will explain what is our solution to this particular problem. So what we built is a thing called blockchain distribution network. The blockchain distribution network, the word itself comes from the content distribution network idea, which is the field that I'm working in. And so a blockchain distribution network is a dedicated network aimed to help blockchain communities, blockchain nodes, to much more efficiently propagate information through the internet. And so to help you understand how this works, so a blockchain distribution network is not simply a better network. I would say it is a smarter network because it does a lot of hard work in the background that I will try to explain next. So instead of simply trying to help propagate blocks faster, which is what some relay networks are currently already doing on the internet, a BDN also sends and transmits transactions through the entire system. Okay? By sending transactions through the blockchain distribution network, it becomes possible to index these particular transactions and to cache this information in the system. Okay? And so instead of sending that famous 540 bytes long transaction, in our system, we use identifiers which are 4 bytes long. Okay? Why is this? How did we come to these 4 bytes? Where 4 bytes can help you address 4 billion different transactions. Okay? So as long as when the transactions are coming, as long as they are not coming in the amounts that are bigger than 4 billions, we are capable of effectively reusing these transactions such that we can effectively serve the blockchain nodes. And so basically, what happens is that once these transactions are distributed to the system, and once all the short IDs are assigned to all these transactions, when a block comes in a blockchain system, instead of the network sending the large amount of information, the large blocks, it is capable of significantly compressing the data so that it becomes possible that all this information is flowing swiftly through the network. So going back to the original case, a 30 megabyte block, which I explained had trouble propagating through the peer-to-peer system, in our scenario becomes a much smaller block, actually 222 kilobyte block, and hence instead of sending a huge piece of information, we are sending a tiny piece of information, which, as you can imagine, significantly helps with propagation. Another technique that we are using is called cut-through routing. And cut-through routing is basically streaming, and I will try to explain how that works. Current blockchain systems are store and forward systems. Store and forward means all the blockchain nodes first receive the blocks. Once they receive the blocks, they have to verify that the block is actually valid. Once they verify that the block is valid, they are going to transmit this block to the next node. bloXroute doesn't do that because we focus on performance, and moreover, blocks in bloXroute in the BDN system are encrypted, and hence there is no need to validate the validity of the blocks. The validation of the blocks helps only at the endpoints and not in the BDN system. And hence what happens here is that we can apply streaming or cut-through routing, which means that as soon as a block starts coming to a to a bloXroute server or the BDN server just starts streaming immediately this block to all other nodes in the system. And so in this particular scenario, you can see here the sending node still didn't finish sending the entire block. This block, thanks to the BDN, is already being received at the other part of the world, where another miner is already receiving these blocks thanks to these techniques. So to summarize, what we are doing is the following. We are significantly shrinking the size of the blocks when they are being sent in the network. And this is not some particularly fancy compression technique, but this is a hard work of transmitting all the data and caching it robustly in our system. And hence, instead of having 1,000 places where things can go wrong, in our system, we simply come back to the 3 links. The first link is between the source blockchain node and the BDN. The second link is within the BDN. And the third link is between the BDN and the receiving end nodes. And very importantly, as you can see, all the nodes in our system are directly connected to each other, right? Now, the blockchain system does not depend on any single miner being malfunctioning or a group of miners malfunctioning. It doesn't matter because we provide, because the BDN provides a broadcast channel that helps propagate this data effectively. The next thing I'm going to show are the real-world results that we were capable of achieving using the BDN approach. And we took Bitcoin, the first blockchain out there. And the logic was, well, if we can help Bitcoin scale, then we should be able to help any other blockchain even more. So what we were doing, we were capable of pushing large and frequent blocks. And using the BDN, we were capable of pushing the TPS rate to more than 1,000 transactions per second. To be more precise, in this particular experiment, there were more than 300 nodes. There were more than 30 miners, and all of these nodes were distributed on 3 continents. Hence, we really had a real network. And in between, once we embedded the BDN, we were capable of reaching this particular performance. This is all good and nice, but the issue with any research or with any idea is that once you solve one problem, you open up other problems, right? That's how it works in the real world. So what is the problem that we opened in this particular case? Well, here, the key idea behind blockchain system is that these are decentralized systems, which means that no single entity has the power to stop transactions from flowing through the network, okay? Well, if that's the case, then the real problem that we are now introducing into this system is that if you have this BDN network in the middle of blockchains, then this network, if not designed properly, can be very powerful because it can decide to censor blocks, it can decide to censor nodes, and it can decide to do many different, to delay blocks such that they are not received correctly at the endpoints, and so on and so forth. So, but if this is the case, then the BDN has to address this particular problem, and this actually was one of the key problems that we understood that we have to solve, and so I will next explain how we solve this problem. So the first and one of the most important features that we have here is that the BDN and its administrator, whoever it may be, should not be it should not be possible for this administrator to censor information going to the network. How can we achieve that? So the way to achieve that in our case is that the blockchain node that is sending information to the BDN is encrypting this particular block. And hence the infrastructure, the network itself, has no idea what is being sent in this particular block. Okay? The BDN blindly still serves this particular block. Okay? Once this block reaches the other miners or other nodes in the system, through the peer-to-peer network, these nodes inform the sending miner that they have actually received some block, and they send the hash of that block, and they ask the sending miner if it has, by any chance, has any knowledge about this particular block. Okay? Once the sending miner receives sufficient number of asks from the peers that it trusts, it is going to then release the key, one-time key, just associated with this particular block. These keys are propagated through the peer-to-peer system. Hence, the BDN has no power to stop this propagation. And once these keys are released, all the receiving nodes can decrypt these blocks and actually understand what is in them. Okay? So this is a very, very important and actually essential thing for a BDN, because if we didn't have this feature, then it would be possible for anybody to go on and make the calls on which transactions are going to go into the blockchain and which are not. And in such a case, then it's no longer a blockchain system. That is something else. Another feature that the BDN is supporting, it is actually providing the ability to the endpoints to control, basically it prevents BDN from censoring a particular node. So assume a scenario in which a BDN decides that it's not going to serve a node for whatever reasons, for example, from a particular country or for a particular region or whatnot. In this particular case, basically, the endpoint node can first compress the data, as I explained previously, then send this data to its peers using a peer-to-peer network. Okay? And once a peer receives this particular block from the origin peer, only then will it send this block to the BDN. And hence, by using this indirect communication, it is possible for the peers to ensure that their blocks are actually going to make to the blockchain system. Okay? And finally, the third component here that we are having is the idea of test blocks. So assume a scenario in which a blockchain node is sending data into the network. However, for whatever reason, this block doesn't make it there. It should be possible for each node, even if they're not miners, to be able to send test blocks into the network. So using the encryption, it is possible for any node, not just miners, to send fake blocks that are going to go through the system and still, but this still gives the ability to the endpoints to audit and understand how the network is doing and how it is behaving. So to summarize all of this, and let me give you actually the big picture of how things work in our blockchain distribution network. So a blockchain node simply installs a BDN gateway on its machine, and this BDN gateway looks just as another peer that is simply a neighbor to this particular blockchain node. Okay? And so the blockchain node is simply doing whatever it's doing so far. It is mining blocks. Once a new block is mined, it is going to send this particular block to the gateway. The gateway is first going to compress the data, to compress this block using the short IDs that I explained. Then it's going to encrypt this block, and it's going to send the encrypted block through the system. This information is swiftly goes through the network. Once this short encrypted block is received by all the nodes, and once the keys are received from the sending node, this particular block is first going to get decrypted, then it's going to get decompressed, and the big block is going to be sent to the blockchain node. And hence, from the blockchain perspective, the blockchain node doesn't even see or understand or need to know that there exists any BDN, because to them, the operations done by the blockchain are completely transparent. And so I will skip most of the coming slides, and I will go to this one, trying to explain that the BDN approach is applicable not just to Bitcoin, Ethereum, but is applicable to any consensus system. Why is that the case? In any consensus system, there are some transactions going through the system, and these nodes in a consensus system need to come to the same page, to the conclusion, what is the particular order for this particular blocks. And so the features that we're providing are very generic. They're very simple yet very generic, and it is essential for any blockchain system to have a very strong network and strong layer 0 solution. With that in mind, I would conclude by saying that a layer 0 and the BDN is an essential part for any blockchain system, and so I'm hopeful, and we're making every effort to make the blockchain systems aware of this important piece that we believe is currently missing in the blockchain ecosystem. Thank you very much. That will be the end of my presentation.